Okay, we're going to discuss this idea of gravitational fields and gravitational potential energy, and we're going to compare it to um, electric fields, electric potential energy. But then I'm going to introduce a new concept called electric potential. So, because we live in a gravitational field, we're able to store gravitational potential energy in that field. And we learned last year that gravitational potential energy is in a constant gravitational field anyway, is m times g times h. And our constant gravitational field strength is g, and that's 10 newtons per kilogram. So let's think about the gravitational potential energy of two different guys at three different locations as they increase their height above some kind of a reference, and that reference will be down here at the bottom. And we'll have a guy one who is 60 kilograms and guy two that's 70 kilograms. We did this in class today. Guy one who is 60 kilograms, mg times h for this 5 meters above the ground is 3,000 joules. Guy 2, who's got a 70 kilogram mass, mg times h for him, 70 times 10 times 5 is 3,500 joules. Excuse me. Then we talk about going up to the next height, which is 10 meters, 5 plus another 5 above the reference point. And guy 1 has 6,000 joules of electric potential or of gravitational potential energy, and guy 2 has 7,000 joules of gravitational potential energy. So it's dependent, the amount of gravitational potential energy stored in that constant gravitational field is dependent upon three things: the mass of the guy plus the height of the guy above the reference point here, and also the gravitational field strength. Well, what if we talked about a quantity that is gravitational potential energy per unit of mass? So that's UG over M. And we calculated that for these two guys at these three different levels again. So basically it's just G times H. So for each guy, this would be 50 joules per kilogram at this height and 100 joules per kilogram at this height. So no longer is it dependent upon mass. The gravitational potential energy per unit of mass is just dependent upon a location in space and the gravitational field strength. So any object at this level right here would have 50 joules per kilogram, I'm going to give that a name, of gravitational potential. Notice how it doesn't have the word energy on the end. Energy is in joules. This is in joules per kilogram, so it's per unit of mass. And any object of any mass would have 100 joules per kilogram at this level right here. So that's called gravitational potential. And I want to establish kind of the concept of this idea of potential versus potential energy in the context of something you already know, which is gravitational fields, before we start talking about it in terms of electrical fields. So all I've done is taken what you already know, gravitational potential energy, and divided it by mass to get joules per kilogram. And if you think about this for a second, this idea of gravitational potential energy per unit of mass, I want to focus on the gravitational field for just a second because I'm about to talk about this in the context of an electric field. The gravitational field is directed this way. If the gravitational field newtons per kilogram it is a vector, it's directed straight down because the Earth as a mass, is attracting all of the other mass towards its center. So if we drew gravitational field strength lines, they would be straight down like that. So I could also think of potential in the context of the electric field. So imagine a constant E field, 1,000 newtons per coulomb, and it's created by two plates, a positive plate on top, a negative plate on the bottom. And I've got these E field lines directed towards the bottom of the page, just like the gravitational field lines I had on the previous screen that were also directed down towards the bottom of the page, but those were 10 newtons per kilogram. This is 1,000 newtons per coulomb. And I put two charges in here. I put one that was a 5 Coulomb positive charge. The other's a 10 Coulomb positive charge. And I could move these around. So I could take this guy right here and I could move it closer up to the positive. I can move it further down to the negative. And as I do so, I'm changing the amount of electric potential energy it has. Because if I'm closer to the positive and further away from the negative, I increase its electric potential because it doesn't want to be up here. It would naturally want to drift down here, attracted to the negative plate and repelled by the positive plate. So I give it more electric potential by moving it up here. I give this one more electric potential by moving it up here, but this is twice as much charge. So it would have more electric potential on this side up there than this would on this side. But electric potential, let me change my marker right here. Electric potential energy divided by charge is electric potential. So this is the definition of electric potential. It's electric potential energy per unit of charge. It's got units of joules per coulomb, and it is independent. Let me write it up here. It's independent of the charge size. It's only dependent upon where you put the charge. Location depends only on location of the charge in the E field. And it depends on the size of the charge. I'm sorry, not size, and the strength of the E field. Just like our gravitational potential energy, or gravitational potential depended only on the strength of the gravitational field and the object's location in that gravitational field. So So now let's talk about electric potential in the context of a single point charge. The single point charge in this example is going to be this charge over here, and we're going to put some test charges of different sizes over here, little q, and they use subscripts K, L, M for different sizes of the test charge. And each time we do that, we can measure the amount of electric potential energy that exists in the system that contains these two. Remember what electric potential energy is. It's that Coulomb's constant times Q, and we'll call that Q test right there, and divided by R. And of course the signs of these matter. If they're negative, then it's negative energy, or if one of them is negative, one's positive, it's negative potential energy, and positive energy if they're both the same sign. So electric potential would be this electric potential energy divided by the size of this charge right here per unit of charge. So on our next, there's a little more information. The electric potential, not potential energy, but electric potential due to a single charged object is known as a V field for voltage. It's actually the definition of voltage. So that's why they use the term V field instead of an E field. Due to a single source charge at a specific location, we've placed a test charge at that location. We determine the electric potential energy at that location, and then you divide it by the test charge. So since we used to have Q test in the numerator and now you divide by Q test, it cancels out. So the magnitude of electric potential is just KQ over R. So that's going to be in units of joules per coulomb. And another name for that unit joule per coulomb is the volt. So when we talk about voltage, like the voltage between two terminals on a battery, what we're talking about is electric potential difference between those two terminals on a battery. So that's where the unit of volt comes from. You notice that the potential field, we call it the V field, and the E field at specific locations are independent of the test charge. So the size of the test charge doesn't affect the magnitude of those two things because the test charge is really small compared to the charge that creates the field. Just like the Earth creates a gravitational field, it's really large, and our masses don't affect that gravitational field. We're like the test charge with our mass. And instead, they characterize the properties of the space at that location. Space meaning the properties of that voltage field and that E field are totally dependent on location. What the difference is with this voltage, this new field called the voltage field, the V field, it's a scalar quantity. It's not a vector. It can be positive or negative, but it doesn't have a direction. So we're going to stress that in some of the activities that we do over the next few days. All right, that's it for this screencast. I'm going to talk more about these notes on Monday in our synchronous learning day. We'll kind of review some of the stuff and we'll build on it. So I'll talk to you guys on Monday.